Ready to Sam always beats me to it. All right, so Zach, I'll let you go ahead and introduce yourself, and what we'll do is have a short presentation, and we'll have lots of conversation.
Cool. I think we're aiming for something in the ballpark like 30 minutes plus conversation. And feel free to interrupt. I'm very happy to stretch that out whichever way feels most organic.
Awesome.
Can I share slides?
Yes, please.
Cool. So I took the time, and thanks, Ed, for giving me a little scouting report on the conversations you've been having and some of the talks you've seen around ChatGPT and emerging technology as may impact healthcare. And I thought I'd take, I tried to look at some of the previous talks and think a little bit about what I could offer that would be kind of a complementary perspective. And my sense is that you've seen a lot around sort of broadly what ChatGPT does, what its anticipated impact might be, and maybe a little bit less around, obviously me coming from the technical academic perspective, around sort of what it really is, according to what principles it operates. And so I want to take the opportunity to maybe situate ChatGPT in broader kind of like the modern generative AI phenomenon in a slightly wider scope of the history of artificial intelligence research, and to give a sense of, in sort of a little bit of like what's different, what's the same, what matters, what doesn't, what's the role of data, what's the role of talent, what you should be worried about, what you shouldn't be. In a way that I think this kind of historical view can give that perspective, and then maybe to look into healthcare applications, and maybe to draw a little bit of a fine distinction between things like clinical decision support and some of the other areas where there's a potential impact. And I'm in a special position to talk about one of them in some amount of depth because I'm now the Chief Scientific Officer, and I direct all the technology efforts at a startup called Abridge, and we're in the clinical documentation space. So we're not trying to make decisions for the doctor, but rather we're trying to help liberate the doctor from spending the entire visit staring at the computer screen and allow them to have more face-to-face time with a patient and get really quickly to a 90% of the way there draft of an after-visit summary that's ready for a doctor's final touches. So here's a place that I like to start these talks sometimes, just like a 30,000 foot view. So I think really there's a wider history of AI, and I'll come back for that past, but largely why we're talking about, I think that the moment when suddenly like AI became a common word in just general sort of every industry sort of thought leadership of what's our strategy, how is it affecting us, how do we need to think about talent, how do we need to think about the future of our business, I think really is a kind of sea change that started with a wave of developments in what we call deep learning. And so this is a series of breakthroughs that happened in around, I'm going to say, and there's a lot of deep personal rivalries associated with what is called, the watershed moment. And I guess the date you pick might imply who you think represented that. But I'd say broadly in the, there were the first signs of something big happening in the late 2000s. And really, I think this became a broader phenomenon with industrial significance around 2012 or so, with the biggest breakthroughs in computer vision. So we had suddenly, things that were like a field that had a kind of humdrum existence of little incremental year-over-year improvements had sudden, 50%, 70% type drops in error rates that suddenly signaled like there was a kind of a paradigm shift in the field. You started seeing, the story when I started my PhD in 2013 was deep learning. It's like certain neural networks are still kind of, a bit iffy. You shouldn't work on neural networks, except for if you're doing computer vision. But otherwise, it's not very principled. You shouldn't work on it. And then sure enough, You started having major breakthroughs in natural language processing or in reinforcement learning. Many of you might have seen, some of the watershed moment where a machine system beat human at the game of Go, which was a milestone we didn't think we would reach for many more years. A crucial part of this was the way that deep learning was used. There are breakthroughs in speech recognition. You might notice that if you were using speech recognition in, say, 2008, it was virtually unusable. And largely to the extent that we can do anything with like virtual assistants, it's on account of just these massive breakthroughs. And these are all powerful, all powered by deep learning, which basically just means large neural networks. And of course, there's the star of the hour, which is what everyone's obsessed with, ChatGPT. So I gave a couple sentence introduction to kind of just say what my remarks would be about, and asked a ChatGPT powered by an underlying language model called GPT-4 to write my opening remarks. And here's what it came up with. Not so far off the mark, eventually kind of veers into some other land from where I would have gone. But I don't know that I would reference the fourth industrial revolution, not my style, but clearly the capacity that we have now for generating plausible, lucid seeming prose in response to certain directed queries for what we're looking for is in a place that's just radically more advanced than where it was only 2 years ago. And this is rippling through kind of all natural language-based technologies, everything from machine summarization, machine translation, and you're seeing it in lots of ways. Now I wanna get to what is this term generative AI? What do we mean by generative AI, and how does it sit? And I think it's a weird category. It's kind of like what do they call it? Like wastebasket diagnoses, where you have the wrong category. It lumps together a bunch of things that don't really share. They don't sit on common cause, or they're not really a proper taxon on the phylogenetic tree. We're sort of have a little bit of a wastebasket category here, but I think it actually isn't totally. I think there's two common threads that make this word generative AI a useful term, and I'll get into it. But I think it's largely one is that we're used to predictive models that take input, which might be simple inputs like tables in a spreadsheet. It might be really complicated inputs like high-dimensional radiologic images, but spit out a very simple kind of output like a classification or a numerical value. And in this generative world, we're producing the outputs of our model are of a different form. They look more like kind of media artifacts, raw documents, whole images. Another side of the generative AI story is this notion of generality that I think pervades a lot of these models, that a lot of these models are trained on internet scale data, and then afterwards, post hoc after training, put to more specific ends. And these two things are coupled together, even when like the actual innards, for example, models that are generating images and models that are generating text are operating on very different principles from like, if you look at the neural network architecture, that they look quite different, but this is like, I think the two big pieces of DNA that they have in common. So let's start now, very foundations. When I say AI, what do I mean? Term is badly overloaded. I think the common usage now, AI when it was coined was basically a specific group of people who wanted to do a particular kind of research and wanted to differentiate with some other group of people who were called the cyberneticists. I'll get into that in a minute. But when we say AI, we're not really referring to that group of people. We're even referring as much to the legacy of the cyberneticists of the AI community. We're using the term in a much broader kind of way, not in its original usage, but just broadly to refer to the science and engineering of building computers that behave in ways that we thought required intelligence. It's a nice term. It also explains like, what is it that holds this community together? Like, why are these groups of people still calling themselves AI researchers, even when the fundamental nature, the technical nature of the methods is changing decade over decade? Like, what makes them stick around? And I think it's this fundamental motivation versus someone who's someone who's an AI researcher will be an AI researcher even when the methods that are the best methods are not statistical in nature, but maybe someone who's a statistician at heart is going to be a statistician whether or not that's what's pushing the frontier of what we think of as AI technologies. And we certainly have come out of a period where it's often been hard to distinguish the boundary between AI and statistics. Now, machine learning is that part of AI, that approach to AI that is of the most statistical nature. It's where we're concerned with making algorithms that improve their performance as measured by some evaluation metrics as they acquire more experience. And these are all kind of general terms. It's a broad framing, but experience could mean just getting more data. Like systems that have more data get better at the task. But there's also interactive systems like robots, where experience can mean not just I get more sort of offline data, but more like interactively collected data as a result of the model taking actions, receiving feedback. And different types of machine learning systems have different sorts of outputs that are assessed by different sorts of evaluation metrics and require different sorts of experience to learn, but this is a nice generic phrasing. So, brief history of AI. We've been sort of concerned with how to do these things that we thought required human cognition since the dawn of computation. Sorry, the mail just arrived and my puppy gets very excited. Okay. Sorry about that. Okay, brief history of AI. 1945, ENIAC, first general purpose computer created. Already a lot of the fanfare around it starts referring to it as an electric brain. 1948, Norbert Wiener is publishing Cybernetics, already very concerned, not necessarily even thinking principally about digital computers. He was coming out of more working on things like trajectory guidance systems for the military in the context of like World War II, but thinking a lot about technical work and machines, doing some of the things that organic beings and humans do, thinking a lot about things like feedback loops, statistical principles. 1950, Alan Turing publishes a paper on computing machinery and intelligence and starts already asking sort of like, we have these machines that could do some of these things that previously, no machine could do, but humans could, maybe even just certain kinds of sort of more like mathematical operations, but he already starts thinking, how far can we go with this? Can machines think? What would it mean to make such a claim? Can we assess that claim, or can we instead like substitute it for something that's easier to assess? Like, can a computer pass for a human as assessed by a third party who doesn't know who they're interacting with? And that's the origins of the fabled Turing test. 1955, a group of people, these are the other community, although truthfully, the boundaries between them are not as clean as like the reductive version of history might suggest, but this is a group of people led by a researcher named John McCarthy, propose a summer workshop to basically solve the grand challenges of artificial intelligence. These guys are a little bit more focused on concrete tasks. They're focused on things like computer vision, on natural language processing. The methods that they grew into to be kind of espousing as the way to go maybe didn't last. These are more expert systems, rule-based systems. But their kind of task orientation in some ways like actually stuck around. Maybe in some ways we're using the like Wiener's methods and going after McCarthy's sort of industrial vision. 1957, the Rosenblatt's perceptron is published. Rosenblatt, and pardon the typo there, I just realized that, not Rosny-Blatt, but Rosenblatt, was a researcher, a psychologist, I believe, but a member of this consortium of cyberneticists. And basically the system works very similar to a modern neural network in that you encounter a data point, you get an output from your model, you compare it to like what should have been the output, the desired target, and you compare them. And if it was different, you make an update to the model. And the system is accompanied by a bunch of fanfare saying that soon perceptrons will be walking and talking and doing everything a human child could do. But again, people were getting a little bit ahead of themselves. Fast forward to 1989, modern neural networks start to take their form. These are larger scale models, multiple layers, and people figure out efficient algorithms for training them. Still same basic idea. You feed in some inputs, you generate outputs that are of the form of the predictions you're trying to make, you compare them to some reference outputs, and you update the model to make your model do a little bit more, what you want it to do. variations of neural networks, different architectures, specialized to different types of complex data start coming out. So Jan LeCun trains ConvNets. These are convolutional neural networks. So it was the first big kind of breakthrough in applying neural networks to computer vision. They come out. 1990s, sort of like textbook machine learning starts coming into focus. You start having this kind of framing of like the dominant ways of doing machine learning, or one, you do supervised learning. This is you're given a data set of collections of X, Y pairs. X are the inputs, Y are the targets. So think like images, labels, documents, labels, characteristics of homes, what price did it sell for? And then you use these to fit a model whose job is to predict Y given X. Then there's unsupervised learning, which is sort of like you just get a ton of data, but not necessarily any labels associated with it. And the question is, well, what could you do with it? And at the time, people are focused on things like clustering, finding little natural groupings in the data. And there's reinforcement learning, which is the idea is you're not given the Y exclusively. Like you have to propose a Y, like in chess, you choose an action, and then ultimately you find out, did you win the game? But nobody ever tells you just what was the optimal move. You have to learn by observing, hey, I took a series of actions. This was my success. And you have to back out to, should I make an update to my policy? In all these cases, I want to contrast 1990s with now. And even as recently as 2010s, the picture back then was supervised learning was 99% of what we're doing in industry. That was where all the action was. And that everything else was kind of like a nice idea. It was a nice academic story, but it wasn't the bulk of like what was actually useful, industrially applicable machine learning. So where do things start to change? So first in 2010s, the big change is the rise of deep learning. Deep learning means people had not just had neural networks, but they suddenly were able to train them much, much more efficiently. They had much larger data sets because storage was cheap, and you had all these internet businesses that are just logging all the data. So you have millions or billions of images on Google image search. Each company has their own business on their own customer behavior. You start having electronic health records get adoption. So suddenly data sets become much larger. And also computation gets much cheaper. And in particular, something called GPUs, which are really good at parallel programming, which turns out to be that the core rate limiting step in training a neural network is very easy to parallelize. So you can take advantage of parallelism by having a GPU with hundreds or thousands of cores to go much faster. You start seeing a lot of promise in deep learning. 2008, there's a guy named Jürgen Schmidhuber in Europe and his student Alex Graves. They start winning some competitions with recurrent neural networks. Then 2010, there's predicting binding sites for drugs that Jeff Hinton, who you might have seen on the news a lot. His students start winning these competitions. 2012, there's the giant ImageNet breakthrough in computer vision. 2014, it starts spilling over into speech recognition. And around that time, you also start having spillover into natural language processing. This is where you start going from, it hasn't touched natural language processing to, within a year, that's almost all anyone at a natural language processing conference is doing. So what's the generative term? What do we mean when we say generative AI? Oops. So largely what we're talking about with generative AI is models that produce not just like a prediction of like, here's the label, but produce these like more kind of seemingly unstructured outputs, images or text. In the case of text, actually, if you look under the hood, you look really closely, this generative AI actually looks exactly like supervised learning, because the formulation of the task is look at a random string of text sampled from your data set and just try to predict what is the next token in the text. I use the word token. Token could be you could represent text at the level of characters where your vocabulary is very small, but the length of your documents is very long because it's one for every character. You could represent text at the level of words where your documents are a smaller number of tokens, but there's a much larger vocabulary of tokens. In reality, we use this less intuitive concept called a word piece, and that's how ChatGPT and other state-of-the-art models represent text, kind of everyone in NLP these days. It's something between a character and a word. Your vocabulary is in the middle, maybe like not a million, but like 50,000, bigger than the number of distinct like ASCII characters. And these models, all they are trained to do is predict the next word. You could think of like token as a word. The job of the model is predict the next word. But that gives a model a generative capacity, because if you're really good at looking at some prefix, some antecedent text and predicting what's the next word, then you could just take that word, append it to the document and say, okay, advance the cursor. Now the document wasn't 200 words long, it was 201. And the last one is the word you picked. Predict the word after that. And if you keep iterating this process, you get, the next word, then the next word, then the next word, then the next word, each one paying attention to what were the ones that came before. And so initially, like this is an example of the output from another paper from Jeff Hinton and his student Ilya Sutskever, who's one of the co-founders of OpenAI. And you can see the outputs from the models in 2012 are, they start looking like text, which is impressive given that the model had no notion of words. This model was trained actually at the level of characters, but they're not that useful. It's still a little bit babbly. But people start improving these models a lot, and they start realizing that, oh, if you train this model where you don't just feed in any text and just predict the next one, but you start off with, say, you've encoded a sentence in English, and now you try to predict what's the first word of the French translation. Okay, now I'm going to feed that back into the model, predict the second word. Now I'm going to feed that back in the model, predict the third word. That eventually, like, you could train a translation model like this. And this kind of model, where you just condition a language model on some input, is sort of what underlies like the modern Google Translate. And so we've been on this bent towards this generative flavor of AI really since 2014. That's probably already the year that this starts taking over commercial machine translation systems. But even in those cases, people are still really focused on specific applications, like training on a giant collection of English/French sentence pairs. So they're just training a model to do translation using only like data suitable to the translation task. And that's something that's about to change. People start realizing you could condition not just on a sentence in English or a sentence in French and generate a sentence in English. You could condition on a representation of a photograph and generate a sentence in English. And so you start having these cross-modal generative things where you get things like image captioning, describe an image. You can imagine now people are talking about these things in the context of, say, radiology, where you say, oh, I could actually, even if we don't have structured data, if I have the reports, I could try to train a model to take an image and just generate what I think the report might look like. People start coming up with models for now, not just taking images as input, but generating images. And these are the generative adversarial networks. This is what they looked like in the original 2014 papers. This is what outputs from these models looked like in 2015. This is what outputs from these models looked like in 2017. And now generative adversarial networks aren't even the state of the art. So when you see the images coming out of like DALL-E or Midjourney, these are generally coming out of something called a stable diffusion model. So one big change has been this moving from predicting these like kind of simple labels to predicting these complicated objects, documents, and images. The other thing is people started figuring out that there was interest in not just training models on specific task-specific data set. Like, I want you to generate this kind of image from this kind of caption, or I want you to generate a French sentence given an English sentence, but actually finding ways to train models on something approaching all the data on the internet. And this is where you start seeing the move towards so-called foundation models. 2018, BERT is sort of trained on something like web crawl to learn representations that are then useful for doing downstream classification, where they basically pre-train this model as something like a language modeling objective, but then they fine-tune it to these different tasks. 2018, OpenAI releases GPT, the original GPT model, trained on web scale data. They're not saying, oh, I want to make something that looks like Wikipedia articles. They're saying, I want to have a model that's just trained on any random sequence of text from the internet and tries to predict the next word. Then they released GPT-2, then GPT-3. These models are successively larger. I noticed in a previous talk, somebody said these models have 100 trillion parameters. That's actually off by a factor of 100, but the best guess people have of the size of GPT-4 is that it's about 1 trillion parameters. So these models start getting bigger and bigger. I like to make a little call out here that people say things like, oh, it's bigger, therefore it's more complex or something like that. This is a big hand wave. The truth is no one, and I mean the very deepest technical theorists in this field who work on this problem all the time, trying to understand the relationship between the capabilities of these models and the number of parameters. We're not quite sure why these models need as many parameters as they do. In fact, our best guess is that they don't need anywhere near as many parameters as they do in order to exhibit the behavior they do, but it's that it's easier to train the models. So often, even once the models are trained, they can subsequently compress them without using nearly as many parameters. It's all shrouded in a bunch of deep technical mysteries that I'm not going to spend this talk zeroing in on. But this is it's sort of an empirical discipline. People found that as we made these models bigger and bigger and trained them, we were getting more and more capabilities. And that seems to have gone to a certain extent, but also seems to potentially be petering out a little bit at the extreme scales that we're getting to. It's a weird regime. The models have so many parameters that it doesn't actually make sense from like a classical statistical perspective. Like you've got a billion, you've got a trillion words in your corpus. Why do you need more than a trillion parameters in your model? How can you even fit that without overfitting wildly? But this is all empirical. We don't have great core foundational principles for why these models exhibit the capabilities that they do. And that's, I'll get into why it's important when we think about them. We think about evaluation, that at the end of the day, you don't start from, oh, these models have lots of parameters, therefore I assume they have certain capabilities. You need to still operate in the same way you do with any predictive models. What do I want to use it for? Has the capability been demonstrated? And sort of how do I go about doing that? And that ultimately, even if a model is trained on like massive generic corpus of online data, if you're planning to put it to a particular use, you still need application-specific data, if only to verify that it has the capability that you're looking for. So let me tell you what you do with these large language models. And basically what people found is you train these large language models, not on a focused corpus oriented to a particular task, but just on all of the internet data. It turns out that you can actually take that single model just trained on the entire internet and actually elicit a lot of very specific behaviors, sometimes at close to the level of the best purpose-built task-specific models, just by being smart about how you invoke the model. And you can imagine the way this is, the model's really good at predicting what the subsequent text will be. And it's seen such a wide variety of text from the entire internet, which includes language learning websites, it includes all sorts of things, that when you then go to the model and say, here is a sentence in English, colon, and you write like, my feet hurt. And then you say, here is the corresponding translation in French, colon. The model tends to propose something that is reasonable, that it turns out, even though the model wasn't explicitly trained on translation data only, the fact that it's so good at anticipating what is the likely autocomplete, that it's actually, if you design what is the antecedent text, you can get the model, you elicit from the model often the solution to these downstream problems. Now, the exciting thing about this is that you suddenly have the ability that there's this repertoire of ways of getting models to do things without even necessarily having much of a data set. And sometimes it's you just give the model a set of instructions. The following is a movie review. The sentiment of the movie review was colon, and it'll say positive or negative. There's a whole repertoire of ways of messing with what text you give to the model to elicit what you want afterwards. And when you hear about in-context learning or few-shot prompting, this is a technique where you feed several different examples to the model of the kind of input-output behavior you're looking for as part of the antecedent text. So you're basically saying, here's X1, here's Y1, here's X2, here's Y2, here's X3, give me Y3. So there's lots of these different techniques where they're tweaking the behavior of the model, not by changing the parameters of the model as we would normally do in machine learning, but actually by tweaking what is the context that is provided to the model. So there's this interesting change. You could view with like a zooming out to this wider arc, you could view classical machine learning training classifiers consisted of a lot of feature engineering. Early first generation deep learning, so much of what people were doing was not engineering the features, leaving the features in a kind of raw state, but engineering the neural network architectures. Now, a lot of times what you're doing is you're getting an off-the-shelf model.
Yeah, are you with Chris?
Hello?
Okay, do you?
You're okay, Zach. I just muted her.
Okay, right. You're getting an off-the-shelf model, but the set of levers is not the parameters, it's not the feature engineering, and it's not the parameters to the model or the architecture, but it's actually the input, this prompt that you design. That's not to say that prompt engineering is taking over. The pendulum is kind of swinging back. Open source models are suddenly now kind of competitive with some of the larger models, and they give you lots of other possibilities because you could actually take these things, fine-tune them, train them in various ways. But I hope this gives you some sense of, and now when it comes to healthcare applications, this is where some of the opportunity and risk is. It's very exciting that you could get out of a model really complex behavior without even necessarily having a data set, just by having someone who messes around with how you fiddle with a prompt and then tries some examples and gets output from the model. But the challenge is, how do you know that this model actually works? For example, in my case, we want to generate coherent, reliable medical summaries for every doctor in every specialty and every noise condition and all kinds of conversations. If someone is just fiddling with prompts and then looking at the outputs and saying, oh, those look, for a handful of outputs, say, oh, that's a cool demo. The challenge is, well, how do you actually assess it? How do you make a statement about the reliability of the system? How do you know among the infinite number of ways that you could try to instrument such a system, which is the best one? And is it even the best thing to do prompt engineering at all, or should you be doing something wildly different, like fine-tuning based on proprietary data sets? And the only way to answer these questions comes full circle, that like, actually you do need data, and you need data if only to evaluate. And that's sort of always been the story of machine learning, is I've got some set of controls, some set of knobs that I could turn that change the behavior of a system, and I have some data set against which I can evaluate such a system. And now there's lots of ways in which these foundation models and large language models change the nature of the knobs that we're turning, and sometimes even change the nature of evaluation because we're generating different kinds of objects. But it doesn't change that bigger picture that at the end of the day, if you want to say this system works reliably in such and such settings for such and such stakeholders, and to be sure that it works across locations and that it works across subspecialties, and that any of these kinds of assurances that you want, then ultimately the validation you're going to get is empirical. And that ultimately does require not just that you saw an impressive demo, but that you have a competent science team behind it that is developing reliable technology. Now, I like to get into what I do at a bridge for a couple minutes, but maybe I think we're mostly on track. Like maybe we'll be at 40 minutes instead of 30. So I would like to start by stressing that there's one thing that's so exciting about these large language models and the way you could use them is how general they are. You're limited only by your creativity of, well, what can I put in some antecedent text to see what comes out of the output text? But that there's actually some very, very, very different sets of problems that can be expressed that way. And the reliability of these systems and the risks associated with using these systems can be very different across them. For example, if I just say, here's a description of a patient, tell me how to treat them. You're asking a model not to distill content that was already present in the antecedent text. You're asking a model to conjure out of thin air based on general information on documents on the internet that have been posted over the last several decades, the answer to this question. You're asking a model, in some sense you're asking, people use the word hallucinate in a funny way, but in some sense you're asking the model to hallucinate, in that you're asking the model to speculate. Now that's very different from a task in which you give a model a doctor-patient conversation and you ask the model to produce a certain focused, distilled summary of a particular aspect of the conversation in a particular format. And there's maybe like multiple differences. One here is a difference where on one side, you're getting on the decision-making side and you're outsourcing a certain kind of agency to the model, which is a capability that actually hasn't been demonstrated all that effectively in the model. Versus on the other side, what you're doing is more working on the clerical side and the efficiency side. But there's also a big technical difference. On one hand, you're asking a model to conjure out of thin air a treatment plan, versus on the other side, the doctor's already said the treatment plan. The treatment plan is already present in the transcript, and you're trying to capture it into a note in the style of like an archetypal after visit summary, so that the doctor doesn't have to make too many edits to finalize. And these are fundamentally different tasks in terms of level of difficulty, in terms of level of maturity, and in terms of the availability of ground truth data against which to evaluate. So, quick, and I only have a few slides here because I wanted this to be more informative than pitch oriented, but I do want to, after talking to Ed, I thought it'd be good to talk about a specific application of lots of these technologies. And so I'm very happy to answer very specific questions. I'm not going to go into the technical weeds of how we build each component, but I work at a company called Abridge, and here I run our technology teams, our engineering and science teams that are building technology based on these kinds of underlying capabilities. The ultimate problem that we're trying to get at, and you've probably heard the story before, is physician burnout. And it's one of the sort of biggest leaders that physicians exit, one of the biggest causes of physicians sort of being dissatisfied, exiting the profession. It's one of the biggest sort of cost sinks. Doctors, according to, there was an article in the New York Times that if doctors did all the documentation they're supposed to do at the level they're supposed to do it, they would have 27 hours of work per day. It's been a kind of recurring story. There are some estimates say doctors spend something like 50% of their time doing documentation in the EHR, especially writing notes. And so the space that we entered, and this company was founded 4 years ago on this vision, before the current wave and current set of capabilities, but already getting deep into this story, is that sort of upstream of everything in the doctor-patient interaction and a treatment plan and ultimate downstream medications and billing and everything, upstream of everything is a visit. And the most important visit and the most information-rich part of the visit is, especially in the era of widespread telemedicine, but even before that, is a doctor-patient conversation. That the conversation is the richest source of information in the clinical encounter. And the idea is, if we actually could capture this, and it turns out patients are actually already recording their visits somewhat regularly, which is, I think, led to a willingness in institutions to say, well, if it's being recorded anyway, we'd rather have a copy of it ourselves and rather derive some value from it. That we'd be able to take recordings of doctor-patient encounters and provide some value to the patient and some value to the doctor. And the value on the doctor side is to lift this clerical burden, and the value on the patient side is to help people navigate their care journey. So to remember, to be able to go back and say, oh, here, actually go back and revisit their visit, to pull out the meaningful moments in the conversation, to say, here's where you discuss medications, to be able to click on a medication, get an explanation of what it does at a 5th grade reading level, to remind people you talked about a follow-up visit. But on the doctor's side, the hope is to remove this burden of the after visit documentation, and to put us in a situation where, yes, the doctor's judgment is absolutely necessary. There might be things in their head that weren't captured in the conversation, but you could think of it as if you had an amazing intern in the room who was listening to everything and taking meticulous notes. So the doctor should pay attention, should edit the note. We're not like Tesla. We don't run around and talk about full autonomy. We talk about keeping doctors engaged and in the loop. We're not trying to replace their judgment, but we're trying to reduce some of the drudgery and allow the doctor to kind of operate at the top of their license and spend their time focusing on the patient. There's a lot of components to building a technology stack like this, and I'm happy to take any questions, but at a high level, we have to capture a reasonable fidelity recording. We have to get it in the background, asynchronously processed, speech to text. We had to make our own innovations in speech to text because commercial offerings aren't as good on medical conversations as we really wanted them to be. After that, there's a lot of important things that are discussed in medical conversations, but there's also a lot of fluff that goes on that's not necessarily medical conversation, but more, bond building, how was your golf game, kind of stuff. And it turns out filtering out medically relevant versus not medically relevant conversation, and even being quite a bit more granular than that, makes a big difference. Then there's components of our models that do abstractive summarization, taking collections of evidence from the conversation related to specific topics and translating that from what raw dialogue looks like to what a polished summary looks like. And then finally, that's not enough. It's not enough to just say, here's a summary, enter it into the record. We also need to have guardrails that check for the possibility of any information being introduced in the summary that wasn't really present in the underlying conversation, tools that make it easy for doctors to take a summary sentence and say, this has happened to me yesterday. A patient talked about a hip replacement, and the doctor at first was like, wait a minute, they didn't talk about a hip replacement. And then they were able to click on the summary where it mentioned that, and it pulls it right back immediately to the sentence in conversation where they talked about it, and you could press play and hear it. And the doctor says, oh, actually, wait a minute, they did talk about the hip replacement. Good catch. And so part of what makes that possible, rather than the doctor just deleting that sentence because they don't remember it, is having really strong verification tools that build trust, the ability to, in an instant, go from a summary back to the underlying conversation. And again, that comes back to this conversation about the difference between asking a model to like wildly speculate about what might be an effective treatment versus distill information that was already there. When the information is in the conversation and our job is distilling and producing this efficiency and documentation, the source material is there in the input. We ultimately have the ultimate source of provenance is the audio recording. This is a place that we can operate where you don't have to just trust the model output on blind faith. We can give you the verification tools to take anything that you have any doubts about and immediately check it against the source. But when you ask a model to just speculate about a treatment plan, you're asking it to call upon all the information in the internet. And at the end of the day, you don't have that ability to trace back to where does that come from the way you do when the ultimate source of evidence is in the input itself. So this is how we're working. Here's a kind of high level look. This is not a real patient, obviously. It's being seen by David Bowie, MD, by seeing Patrick patient. This gives you a sense of what our recorder looks like, what the corresponding documentation looks like, and also some of the tools that we have for navigating not just the note, but checking things against the transcript. So happy to stop here and keep this interactive, and I hope I didn't go too long, Ed.
Zach, it was wonderful information. I can see you can not only have enough information for a course, I would imagine you can do course 511, 512, 513, 514. I mean, you have a lot of content, and that's very, very valuable. So thank you for all that. I have a couple of questions. Actually, I always have a page of questions, but I'm going to weave in other people's thoughts as well. But I'll start with just a few, and then we'll turn over. Janice wanted to talk to you live on this as well, and we'll take other questions as well. You start off with something that was intriguing. When you asked the model to come up with your introduction, and he said, it wasn't just my style. And it's funny that you said that because I have a friend that just said that she was going to go ahead and allow for ChatGPT to write his essay for his class. And it wasn't going to be able to be passing because they knew it didn't sound like his language. And, how do you go ahead and insert style? Is that a parameter that you'd have to build out, or?
Right.
Yeah.
And we encounter this all the time. It's very easy for someone to just get ChatGPT to say, like, here's a snippet of a conversation, summarize it. And you look at it, you're like, oh, it kind of is a summary. But if you actually go with doctors, they're very, 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 very particular, right, about what actually is the ideal. And there's even some amount of genuine disagreement, but there's also, quite a lot of consensus about what you want in some of these sections. There's so many ways you go about it. One is that obviously, like, within the realm of prompt engineering, that look, every different prompt you put is going to elicit notes that, are going to have different characteristics in terms of how consistent they are in style, in terms of both how variable they are in style and also what that style is. So there's a whole lot of everything turns towards, okay, well, how do you use the prompt to getting the style you want? How do you evaluate? How do you sort of measure these things over the course of a sufficiently diverse corpus to make sure you're actually getting the style that you want? how much can you get from automatic evaluation? How much do you need human in the loop evaluation? There's within a prompt world, for example, one thing that we do is provide examples. And when you provide examples, it's important the examples conform to the same kind of style as the sort of thing you're eliciting. But it goes way beyond that, because then ultimately, sometimes like we exceed the capabilities of these models. And actually the way we're able to get the style that we want is because we've maybe, so many steps. Like you can imagine, like you actually are able to use some models to get you like in the ballpark of a summary that's succeeded by like a human QA effort that will transform things to exactly the style you want, which is followed by a fine-tuning step. There's so many different ways. There's times sometimes where you have the output that you want, where you actually have you have the exact information that you want in a proprietary data set, but you don't have it in the format you want. And that's a situation where, like, for example, GPT-4 can be very effective at doing certain kinds of format conversions, and then you can take that and distill it back into where, like, the job of that model isn't to do the input to output, it's to do output in format A to output in desired format B.
Yeah.
And then you're able to turn that back into a learning. So we have so many different tools, and it's such a rapidly evolving landscape. And I think that this is an area where broadly that there's a danger of, like, a lot of companies are popping up that we call them like internally, we call them thin layer LLM companies. It's like basically a pure commercialization play that is a very sort of thin scientific effort that's just sort of like all it does is call ChatGPT in the background in a kind of naive way, without proper evaluation, without the ability to do something else if something else is more effective. And I think for us, the singular focus has to be is like what performs best, what is most reliable. And then there's this very rich palette of ways of getting there that's rich and constantly evolving, and we're kind of willing to chase it down.
And Zach, you had mentioned something that was pretty profound in our last conversation, where you called models that you had built yourself. And now some people are developing software calling ChatGPT without testing the results. And just get your quick reaction there before we turn over to Janice.
Right. Well, I think the thing about things like ChatGPT is because you can get something that like passes like the very first sniff test, sometimes with no data at all, just by, you give it a set of instructions and you get something that kind of looks like it used to be, if you were thinking of the world where I have a randomly initialized neural network and then I feed in inputs and the targets, if I don't have any labeled data, I can't get off the ground. I have nowhere to start. ChatGPT and tools like this give us that, like, where you can get without being a serious player, without actually having data, without doing evaluation, without having any training data, like the floor of like where you can start has been raised significantly. But the fear is that there's a lot of people out there that don't really know that that's all they're doing. And so that they can get out something that has like the whiff of a capability, but without necessarily really having the goods to back it up, or the scientific rigor to make sure not just that it's like, oh, models can sort of do X, but actually like we're doing X in a way that is, capturing 90-something% of the medically relevant, details that are captured in this conversation.
Yeah, a call out to vendors to test. That's the lesson I learned from you. Janice, just take a few minutes, then we'll get over to Zach's question.
And just really quickly before I get into my question, I just want to comment that our experience is that even if you feed in good examples of what you're looking for, getting back out something in that style is not very easy. And actually, this is sort of the gist of my question, because one of the things, and by the way, I'm Janice Karen from the Massachusetts Health Data Consortium. Thank you very much for the talk. One of the things that in our experience, you sort of are giving like it can regurgitate out a summary as almost a given from the way that you're talking. And we found that it's actually very difficult to get a reasonable summary of something from ChatGPT. And at best, and not only that, you get kind of this best case, worst case scenario where a lot of the time you get something that on the surface looks like it could pass,
Sure.
but it's completely wrong, or has, you know, bad data. For instance, we asked it to summarize an article that was talking about a patient's efforts to get privacy violations corrected. And the summary that we got back was all about how great at privacy one of the companies she was complaining about was. It was as if they paid to have that advertisement.
Now that's like pretty extreme, but I would say that overall we're actually completely aligned. And this is my criticism of like the dangers of like the sort of thin LLM approach of like, is that like, just as you said, it's very easy for, when I say very easy, it's not obvious. Like, look, I wouldn't be making such a huge effort, and I wouldn't be running a team of, you know, a very large number of like, you know, amazing machine learning scientists completely like, I don't know what to say, but like, you know, just like nose to the ground, constantly working on how to innovate on this problem if I thought it was an easy problem. I don't think it's an easy problem. I think it's taken a tremendous amount of work from a large group of very talented scientists to get to the level that we're at right now. My point isn't that it's easy, but precisely what you were saying is what's easy is getting to something that very superficially looks plausible. And there's different levels of easy too, right? There's levels of easy, like I messed around with it for 10 minutes. There's the levels of easy that is a handful of software developers and entrepreneurs messed around with it for 2 weeks.
Right.
But those are both very different from the 10 very strong scientists, you know, spent millions of dollars curating a massive amount of like very highly structured data. And on top of that, explored a large family of tools, which include, but are not limited to the capabilities of GPT-4. Having the ability to evaluate on large corporate, you know, like there's these different levels. But what I'm saying is the fear is precisely that, is that it's easy for someone to like fool someone in a demo.
Yeah.
And much harder for someone to deliver the goods on a constant basis. That's been one thing that's been humbling, but also just super gratifying in actually having this technology deployed in health systems, is starting from there's something very different about what wows someone in a demo and what is turning around someone's experience of practicing medicine on like a day in, day out basis. And so much innovation had to go between the level of like people in demo are like blown away to a product is at the level that, and even then, like we kind of, our attitude is always like, we're never there. We're never satisfied. So that's, I think, where we are. And then I think on your other point, I just want to touch on it. Consent is absolutely a thing. So all of our visits, the guidance is that there is sort of doctor and patient have to consent. I think in most states, that's even the standard, that you need 2-party consent for recordings. So this is something that patients have shown are much more comfortable with. And, you know, when I first heard the idea 5 years ago, I didn't necessarily know like how cool are patients with it, how cool are doctors with it. But it turns out that when doctors come and say, hey, they explain it, say, this is an AI tool that will help me write my notes so that I can spend more time in the visit focusing on you. Would it be okay with you if we use this tool? You know, you're totally free to opt out. That patients actually do want this and do consent, and they do appreciate the FaceTime with the doctors versus kind of watching them type with their back to the patient. And there's also been a tremendous amount of willingness on the doctor side. And previously, a very interesting thing is that previously, or even currently, the recording of doctor-patient visits has actually been very common, surprisingly common on the patient side. Patients do it for a lot of reasons. I think they do it because maybe they waited 6 months to see the specialist, and this is their one-off. They get these 20 minutes and they don't want to miss anything. Maybe their son or daughter or husband or wife usually comes to the doctor's visit with them, and maybe has more wherewithal about what's going on, and they want to be able to go and review the visit afterwards because they couldn't come with them that time. And so it's actually, I forget the exact numbers, but it's a surprisingly high percentage of visits that are already recorded. And many of these are actually with the patient's consent, but without the doctor's consent. And so I think part of the hope here is to put it, to get everything kind of above board, and then also to get the most value out of it for both the patient and the doctor.
Zach, yep, Zach, do we have a question from another Zach? And
Oh,
it's
great.
all right, and he sounds very deep into AI. So what are your thoughts on calibration when using proprietary generative LLMs? The methods we use for discriminative models rely on access to probabilities or logits. Hopefully I said that right, which we're not getting from, say, OpenAI.
Yeah, so lots going on there. Right, I think OpenAI used to make probabilities associated with each token available. I think that was also largely because their constituency was more machine learning people who were using it, and versus now I think there's this way that it's a lot of software developers who are less in tune with what's going on under the hood. I think there's also maybe you leak a lot more information from the model when you reveal the full set of predicted probabilities and you do the logics. Now that said, I mean, I don't think calibration is the primary issue. And the reason why is because when I care about calibration, I care about calibrations for everybody's benefit, concerns the accuracy of uncertainty estimates. You know, when I say 80% probability you're going to die, does that really mean that like 80% of the time that I say that someone dies, or does it mean that I'm wildly overestimating or wildly underestimating the risk? Humans kind of famously actually are very uncalibrated sometimes in our prognostications. Like things are, you know, people like Danny Kahneman get to write lots of books about this. I think generally when we think about calibration, the object of interest that we want to quantify uncertainty over is the more big picture, like discrete kind of objects. Things like, right, probability that someone has a disease, probability that someone's going to die. The actual likelihood that this is the next token in the summary is a little bit weird, because the truth is that there's many like these unstructured objects are kind of weird. And there's a million summaries that actually all have the same content. You know, there's like a kind of limitless number of summaries that are all actually qualitatively the same for our purposes. They just have different wording. And so the probability is spread among them all. It doesn't necessarily tell me so much to know, like, okay, the next word in the decoded summary was but the only had a 35% probability. And then I say, was that a calibrated probability or not? I think I'm more focused on calibration from a different standpoint. Now that being said, there's lots of other things you could do with probabilities, including how you decode the model and the kind of fine-grained control you could have if you wanted to, say, decode multiple candidates and do something with them. And OpenAI certainly lets you do some amount of that by like setting the temperature parameter for when you're doing sampling. But there's, you know, when you're going through OpenAI, you're stuck with, you know, what it is that they expose and the set of tools that they make available to you. That being said, I clarify that, you know, a lot of, there are places where OpenAI's power tools are really powerful, and they're the right way to build things. There's a lot of parts of our technology stack and whole sections of nodes that don't go through, you know, that kind of model at all, and we actually have complete control. So yeah, interesting to keep an eye on, but again, I think there's a little bit of nuance into like over which predictions precisely are we concerned about calibration.
Okay, thank you, Zach. We are running really, we've kind of gone over, maybe for just another 3 minutes. We can ask one more question to you. Would it be okay?
Sure.
Okay, Janice, we have one more question from you, then we'll call it quits.
Oh, okay. I actually was going to, I was just wondering, you didn't talk about ChatGPT AI very much, but since you did kind of a comprehensive history, have you seen as much growth in that area? Because I've got to admit, like I used to use old chatbots like Eliza. I don't know if you're familiar with Eliza, and I have not seen a lot of improvement personally. So can you talk about that for a moment?
And so what precisely question, like exactly, like when you say chat AI, just mean generally like improvement
Like
of
a lot of the supposedly the newer chatbots are being driven by some of the large language models.
Sure.
And some of the predictive models to try to determine what people are actually asking about and serve them up the information they want. In my experience, that is an epic failure.
You know, I think my take on this is not extreme hot or extreme cold. Like I'd say, well, like in the first place, ChatGPT kind of acts like a general purpose chatbot. And then there's certainly ways that people are trying to build more purpose-built chatbots on top of ChatGPT or invoking ChatGPT in some creative way under the hood. I tend to think like, you know, there's this interesting space always of like, you know, just new technology hits and there's some people saying like, oh, it's general intelligence and it's replacing everything. And, you know, like you kind of think like AI is solved and there's that wing. And then there's the sort of like other wing that like, you know, I think my friends, Gary Marcus and Ernie Davis fall a little bit into, which is often just being like, it's all nothing. You know, I think they've had to retreat from that position a little bit. I think the reality is somewhere in the middle, which is that I think we have a tendency to see something absolutely amazing and just extrapolate to like everything is solved. And that's not the case, but that also doesn't mean that there's not something kind of amazing going on. And I'll say that like, there are certainly certain focused use cases where ChatGPT has capabilities that really kind of like rock my like previous conception of like where we were. And yet there's also fundamental limitations. And I think a lot of what's happening right now is people feeling out that new landscape, you know, and it's hard because like initially, like if you're looking at some of the things it's really bad at, you're just like, okay. And also if your expectation is this is something like a human interlocutor, and then you're also looking at some of the things it's really bad at, it's like way oversold. On the other hand, if you're looking at like what could we do before and novel capabilities, there are some things that are just breathtaking. And so I'll give an example of, and so much, I would add here that I think so much hinges upon having, speaking of calibration, I would say, to use the word a little bit more informally, having calibrated expectations. So I have a lawyer. A lawyer got a very like specific question from a client and spent a lot of time trying to hunt down the answer to this like very obscure legal question, right? So he looked for it and he couldn't find it. And he spent hours on it and it was very frustrating. And he was searching around on Google. And then he said, you know what? Let me ask ChatGPT. And I know you're probably thinking like, you know, sort of like red flag, like I could see where this goes wrong. But he's not a dummy. So he's not like that guy from like the, whatever was the recent New York Times article about like he's not like the lawyer who like just like took the output of ChatGPT and put it into his brief and sent it off to the judge. And but instead he had he was a little bit more of an adult and he had some intellectual armor, and he treated it like Google search, like a next innovation in that kind of line of information retrieval. He asked the question to ChatGPT. ChatGPT came back with the wrong answer, but the wrong answer expressed in the right terminology and with a link to the article that turned out to be the right article that he needed to find to confirm the right answer. So someone, and I'd like to, just to finish this thread, is like, I'd like to on that side, sort of like, you know, one thing I've been thinking about, I was away in Australia when Ed and I chatted last, and I had a little bit of time alone because everyone's asleep in every other place that I've ever lived, you know, during the day. So I started thinking about like, you know, some blog posts that would be fun to write again. And one thing I realized is there was this moment, does everyone remember like 1998, 1999, when like internet was already there, but was finally starting to really fill up with content and search engines were relatively new. And there was this sort of like attitude that was like, I remember like you put some, you know, someone would, people would hear you say something and it would always be like, where did you hear that? The internet. And it was almost like the takeaway, like there was this one group of people who would like naively just type something into Google, take the answer at face value, no matter where it was, and say a bunch of goofy stuff. But then there was this overreaction on the other side, which was like, if you found the information on the internet, like you're a total rube, like you're being had. And then at some point we realized, okay, like the internet has all the information, including reliable sources, including unreliable sources. And the way to navigate this is like search isn't just type the thing and then take the answer at face value, but it's like this instrument for information retrieval. And once people started forming that set of expectations, again, not everybody made it there. There's still plenty of people who will believe the first thing they see and wind up deep in some conspiracy theory or something. But I think for the rest of us, we developed a little bit of armor about like, what is the effective way to use this? And a similar thing is happening with code. And this is, I think, one of the areas where like ChatGPT is absolutely breathtaking in its ability. Is you could say, you know, like all kinds of routine things that people do in the course of programming, in the course of scripting, you could ask it for code and it'll generate code. And a huge fraction of the time that code will actually run, and a huge fraction of the time that code will actually do what you wanted it to do. Now, it won't always. And sometimes the code will be wrong, or sometimes it'll have a bug, and sometimes you're like, or you'll try to run it and you'll encounter some error because you didn't have the right library and you have to figure out how to get out of it. It doesn't do everything for you. But on the other hand, for people who are getting good at sort of like, you know, same is true of friends and advice in a way, not to anthropomorphize these models, but very often like, you know, like you can go talk to someone, you get some input from them. It's still on you to determine, was that good recommendation or not, or was this actually the answer you were looking for? But there are certain of these interaction patterns. And I've seen people not just like one chain deep, but go deep, like debugging something, getting their machine set up to do some tasks, writing a whole program in a new framework, to the point that they're using these systems in a dialogue type interaction and actually getting to like levels of productivity increases that I think are like significant double digits in terms of like, you know, time taken to perform certain tasks. So I think it's a mixed bag, but I think, you know, like the truth is somewhere in this middle. It's not a panacea. It doesn't solve everything. It's not a human interlocutor, but it's also breathtakingly effective in certain places and when approached with the right set of expectations.
Zach, what a wonderful way to end the call. That was really, really nice to add that balance. Thank you so much for helping us understand some of the AI history and your application and your perspective. That was really awesome. I wish I could take your course.
Thanks for having me. It was great to meet you all.
All right. Thank you, Zach. Take care,
Take care.
everybody.
Thank
Bye.
you.